lambda g, simply send the group element, I mean the principal symbol if you want, to g minus 1. And then the first statement was that this induces a, maybe I write it now today this way, from gr O over fp p g from lambda g. And the second assertion was that the two filtrations, J nu and lambda G nu, coincide. So let's first look at the surjectivity of this map. So this map was L tilde, I think. We do have, so note that, I mean, J nu is J nu plus. I mean, this was defined as a closed module, submodule, generated by certain elements. And so, I mean, if we forget about closed for a moment, I would have to write down here right, I mean, those elements which appear here but do not appear here, and those were the following ones. L plus omega h1 up to omega hs is equal to nu, all possibilities for the h and the l. And then here the module generated by the element p to the l, h1 minus 1 up to hs minus s. And these are certainly only finitely many. Now there is this issue with closed, but because we have pseudo-compact modules, I mean there is a general fact that the sum of two closed submodules is automatically closed again. This is very wrong in general, but for pseudo-compact modules this is okay. This is closed. I made this remark yesterday, and this is closed because it's finally generated, right? That's another fact. Any finally generated submodule in a pseudo-compact module is closed. So we see that gr nu lambda g as an, right, I mean that's the difference. So actually let me write it down immediately for the whole thing. But the gr nu piece of gr lambda g then as an O module is generated by these finitely many elements. But they are products, right, in this ring. So I see as an, and this here sits, so to speak, in gr O. So as a gr O algebra is generated by the elements, right? I only need elements of this form. So just take g minus 1 plus j omega g plus for any g different from 1. But I mean, they are of course visibly all in the image of the map. So all in the image. So it follows that L tilde is surjective.
The finiteness is because you only need representative. You only need finitely many HIs because.
No, I mean they are strictly positive, though. I mean this is the values are discrete. They are strictly positive. I mean the possible S is also bounded.
The question is why have only finally many H such that WH is less than equal to mu, for example?
Because it's a discrete set. The values of omega is a discrete set. No?
Values might be discrete, but the h high is.
Yeah, so for example, if you take QP, there are infinitely
No, but I mean, we have our. I mean, if you think in terms of an ordered basis, I mean, we know exactly how omega looks, right? I mean, right? I mean, h has some expression in an ordered basis, and then omega h was the minimum.
Maybe you only need representatives of G mod GU or something.
I see. Yeah, okay. I have to be a little bit more careful because I only see that the minimum is. Yeah, I think we had, right, I mean, we had this, okay, I see, yeah, but I think we do know somehow that for large, no, but, okay, for, I mean, what you're saying is I cannot argue.
If you replace an HR by HIG for G and GU plus, then rewrite it.
Right. I mean, we do know. I mean, if I take, I mean, the G nu, the elements where if this lies in G nu plus, it lies in here, right? I mean, if H is in G nu plus, then H minus 1 is in J nu plus. Do we know this already? Yeah, the value is always bigger. I mean, the omega tilde of G minus 1, H minus 1 is always bounded below by omega of H. And, okay, and I mean, we have basically checked that that now in G nu, I mean, this only depends on the coset, I mean, the image. Right? If I have now any if I take, so if I have now any G in G nu plus, in G nu, then somehow its value on the right hand side only depends on the coset modulo G nu plus.
Note 3.
Yeah. What was note 3? I mean, this was the computation that this is this was a homomorphism of abelian groups, right? Yeah. Okay, but it's right. I have to say something at this point. Okay, so so the injectivity we will prove somehow parallel to the second assertion, and for that I was asked yesterday after the talk anyway to somehow how one can describe the elements in the universal enveloping algebra. So that's what we are going to use now, the so-called Poincaré-Birkhoff-Witt theorem. But let's first see that we do know, right, that this was proposition 8.4. We do know that the principal symbols of our ordered basis is an FP P basis of GRIL G, and then of course also a base change to K or whatever to GRIL omega. And so the Poincaré-Birkhoff-Witz theorem then says that then, quite generally, I mean, whenever one takes any basis of the Lie algebra, then the monomials, so the ordered monomials, of course they have to be viewed as ordered because in the algebra is not commutative. The ordered monomials in these basis elements form an FPP basis, whatever the ground ring is, basis of the universal enveloping algebra. So, so you see we can conclude from this. Do I have my so this implies various things. So this implies, right, we do know surjectivity already, and the map is graded, of course. So so we see that the I mean, maybe I write it down. Implies that K mu lambda G as a K-vector space is generated by the finally many elements I mean, I have just to look which of these basis elements, right? I mean, they are homogeneous, so in the grading, so which are mapped into the new graded piece. And then, of course, I have to apply because I want to do this over K, I have to, of course, to those, I also have to allow, in addition, I have to allow applying the operator P, which just means multiplying by powers of P. So those elements are P to the L, T1 minus 1. Right? I mean, these are the images of the principal symbols, alpha 1 up to GR minus 1 alpha R for, I mean, they have to sit in the right degree. Right? I mean, this thing here is the image of such a monomial where I have applied the operator P L times. And so it has to sit in the right degree. This means that L plus omega G1 plus omega GR is equal to mu. Okay, so for the injectivity, we therefore need to see that these elements are k-linearly independent. But, I mean, before we do this, let's look at 2i. I mean, so, I mean, this means, so this is 1, somehow 1. And then, of course, we see that we can replace, in this equation, we can replace this sum by the sum over these elements. So J nu is J nu plus the sum. And we have now here just alpha I omega G1 plus alpha R omega GR is nu, or p to the L G1 minus 1 alpha GR minus 1 alpha R. But this shows right. I mean, now these are monomials now in the original definition of the naive filtration. I mean, this was defined in terms of such expansions here. This is a monomial which occurs there, so we know exactly where it sits there. It sits in the newest filtration step. So in other words, this shows that J nu is J nu plus lambda G nu. I mean, the containment of this in here did hold true trivially anyway. We know this already. And now this shows that the difference we can cover by elements in here. But now, because they are, so now by discreteness, of these values where this is non-zero, where here really are jumps and induction, we get that this holds true modulo any bigger index. For any nu prime bigger than nu. Right? I mean, the difference from here to here, these are finely many steps. So in each step I could get something even in bigger nus, but anyway, something in lambda G nu. And so now comes another property, general property of pseudo-compact modules. So, so now by pseudo-compactness, so in other words, we have, right? I mean, we have that J nu is the intersection of all nu prime bigger than u, J nu prime plus lambda G nu. And now this other property, I think we have maybe already used it at the beginning at some point. I'm not sure whether I've mentioned this already. Whenever you have closed, I think I wrote it down. Yeah, I'm not sure. Whenever you have closed submodules, they are all closed here. You have such a decreasing family, and then you add one other module, then you can exchange the intersection and the sum. So this is the same as the sum of u prime bigger than u, j nu prime outside this here. So this is a non-obvious thing, which is due to pseudo-compactness. But now remember that we before this theorem, I mean, we convinced ourselves that this filtration also is separated. So this is 0. This was remark 10.1, I think. This is 0, so this is equal to lambda G nu. Okay. So this proves the second assertion. And now let's go back to this linearly independence business there. So suppose you have a relation. Suppose we have some coefficients, I think they only depend. I mean, L is determined by nu, and I only need to index this by alpha p to the L. Right, is a relation in grill, so this is supposed then to lie in J nu plus, which we now know to be equal to lambda G nu plus. I mean, for some, these are elements in O here, some elements in O. So this means then, right, I mean, this means that the omega tilde of this expression is strictly bigger than u. So, I mean, this sum, maybe I don't repeat it. But now the omega tilde, these are all monomials. This is now written, right, in the form where we know what omega tilde of it is. So this is the minimum over this, with the same index set, and then v of the coefficients plus, this gives of course an L, plus L, plus then sum alpha I omega gi. But you see, I mean, you see that this sum here is exactly the sum here in the index. So this is the minimum over all alpha, and this is always nu. So what remains is here VC alpha plus nu. But this means that, I mean, we have to strictly bigger, so this means all C alpha lie in P times O. And so in the graded thing, so for these purposes, they are 0. So somehow the C alpha becomes 0 in Q O. Okay.
Why is this remarkable? What didn't we know that the intersection of all this J nu is 0?
Yeah, that's what I'm applying here. That was the remark.
I thought the remark
No,
said
the remark was not that.
lambda G nu V form of
Oh, and sorry, it's you are right. This is a typo here, apparently. 10,
What is
yeah, okay, this is a typo. It has to be lemma 10 2.
What is precisely the statement? That if you have a pseudo-compact ring R and some close to sided ideals, or I mean, are J nu
No.
open? In lambda T?
This has nothing to do with ideals. You have a pseudo-compact module.
Yeah.
In it, you have a decreasingly filtered family of closed submodules, and you have another closed submodule. And then the intersection, then somehow in this sum, in this you can exchange, so you take the intersection of a module in your family plus the separate module. It's the same as forming first the intersection of your family and then adding the other module.
So you just require the things to be closed.
Yes. Right. Yeah. Okay. Oh, I see. No, the remark 10, I mentioned here. Yeah. This was I cited here as well. It's no typo in my notes. I just looked at the wrong line. I mean, the remark 10.1 said that they are closed. Remark 10.1 said that the lambda I mean, yeah, I mean, maybe I don't really need this to cite this remark because it's obvious. I mean, I cited here the remark 10.1 in order for that these are closed, but maybe this is kind of a little bit too much because they are somehow, I mean, they are even open, right? The remark says they form an open, a fundamental system of open zero neighborhoods. I think that they are closed is directly visible in some sense. Okay, so now let's go to now let's go back to the question of I mean, we do know that compact p-adic groups somehow provide, I mean, by going to appropriately small open subgroups, provide such p-valued groups. Now let's now look at the converse. So as before, and I mean somehow the attempt to do this, of course, the obvious one in some sense. So we pick an ordered basis. G1 up to GR, G omega, right? And then we have the homeomorphism C from Cp to the R to G, which sends x1 xr to G1 x1 gr xr. And so we simply view, the point now is view the inverse phi of C as a chart, right? I mean phi G into Qp to the R. And then, I mean, if you want to proceed in a formal way, I mean, equip G with the maximal atlas containing phi. I mean, since I won't explain these words, I mean, they may be meaningless to you. Anyway, another way to say this would be, so equip alternatively G is the unique structure of a locally QP analytic manifold which makes C into an isomorphism of manifolds. I mean, Cp to the D, of course, I think, Cp to the R, I think, you will believe me, has an obvious structure of a manifold into an isomorphism of manifolds. Okay. This is the idea. But now, of course, we have to verify, first of all, that this is a group, right? That the multiplication is locally analytic, and then also that this does not depend. I mean, we have made a choice here. That would not be good. We want a natural structure. So that this manifold structure does not depend on the choice of the ordered basis. Let me maybe also introduce as a notation, so I think, I'm not sure, but I think I need this as a notation. Need coordinate functions right, I mean the phi I, so they go from G to QP, and they send, of course, such a product to the xi. And I mean, they are, just to mention that, of course, they are locally analytic by construction. So what we have to do is the following. Before I formulate this, let me make, I mean, the technique of to handle all this rests on the following simple principle in the completed grouping. That's the reason somehow that we have to work into proof now to do what we want to do. It's best to compute in the completed grouping, and therefore I had to have this after the previous paragraph. So for any, so let's convince ourselves of the following simple fact. For any group element and any p-adic integer, we have the convergent expansion. Right? I mean, in the group we can raise the h to any p-adic power. Now we can okay, let me just write it down. So of course the obvious attempt to somehow to expand this in the complete grouping is using the binomial series. So let's convince ourselves that this really makes sense. I mean, first maybe I should recall what the definition here is. So y nu and y can be any p-adic number, or I will later in the next proof I will use even a variable, right? I mean, it's always defined to be y. I mean, just the naive definition, write it down in a formal way. And this makes, of course, sense in many different contexts. And maybe formally, y over 0 is defined to be 1. Okay. So, right, I mean, they lie, of course. Now, if y is really a p-adic integer, we do know that they're all p-adic integers by density. I mean, this is for a true integer. Of course, everybody knows this is an integer, and then the true integers are dense in the p-adic integers, and therefore this always has to be a p-adic integer. So now let's write our y as the limit, right? I mean, as the limit of some integers. Maybe I can continue here. So then we have hy is h lim mj. And this is, right, this was how it was defined. This is the lim of the hmi. This is the lim in G. That's how this p-adic exponent was defined. Exponentiation. But I mean, the map from G into the completed grouping is continuous, so this is also the lim in CPG. And now, of course, we write the individual things. It's clear that we can, maybe I do this in one step, right? each, I mean, I've artificially write this as h plus 1 minus 1 to mj, and then apply the binomial formula, sum mj n h minus 1 to the n. So far so good. And now I exchange the sum and the limit. And this I can do because, so for this here, note that limit, why is it? Okay, I mean, okay, it's this n. N goes to infinity of omega tilde h minus 1 to the n is, right, we do know already from these corollaries, we know this is multiplicative, and then in such an expression, it's the omega of h. So this is just n times omega of, I mean the limit, lim, which is infinity. So, and these are all p-adic integers. So this means these summands somehow, they do become arbitrarily small, and therefore I can exchange the sum and the limit, and now this limit, of course, is the other one. So this is yn h minus 1. Okay. So now then we can it's fallen down. So now let me formulate the technical statement. We have to prove lemma so I take any finite set of other elements, let h1 up to hs and g be any elements. So then for any I between 1 and r, there is a power series fi of y. I mean, and I need the coefficients, so it's sum alpha ci alpha y to the alpha in s variables y equal to y1 up to ys with coefficients in p with coefficients in qp such that 1. So the coefficients get arbitrarily small. Two, if we insert, I mean, this means if I insert here p-adic integers, and I mean the coefficients go to 0. If I insert here p-adic integers, the whole expressions go to 0, so this converges. So then this converges, and it makes sense to ask that it's again a p-adic integer. And finally, H1, I mean, what do these power series do? They do the following. HS, YS, right? I mean, for any, again, for any such tuple, I can take this group element. I think there must be there must be a misprint here. It's the product. Yeah, I think right. This is some group element depending on the y. On the other hand, I must be able to write this in my ordered basis. And so the exponents are given by this power series. So this is a typo here. So this is the claim. So in particular, this says, of course, in particular, that's how we want to apply it. The functions from Cp to the S to Qp, which sends such a tuple to this element, and then applied the ith coordinate function, right, are locally analytic. And they are even given globally by a power series. Okay, so let's look at various. Now let's use this remark twice. So first for remark right. I mean, first we apply to such a product. I mean, an expression according to our ordered basis. And then it says we can expand it alpha. I mean, we use these expansions for the individual terms, and then we multiply them together. Of course, the order has to be respected, and we get this here. And here we have gi minus 1 to the alpha 1 and so on, but the gi minus 1 are our expansion variables. So here we just have b to the alpha. This is already an expansion as we consider in the standard expansion as we consider in the completed grouping. Now, similarly, for this product, except of course now we don't arrive yet at the standard variables, right? We have, say, beta y1 beta 1 to ys beta s, and here we still have h1 minus 1 to the beta 1 hs minus 1 to the beta s. But I mean, those have some standard expansions. I mean, just right. I mean, write them down. So they are standard expansion. So it's, I mean, beta is fixed here, but then we have the running multi-index alpha. We have certain coefficients, alpha, beta. They depend on both, and then we have our standard variables b alpha. And so we do get h1 y1 hs ys is equal sum alpha, sum beta. Now these binomials here. And then, okay, times c alpha beta, and then e alpha. Okay, so now, so this is, okay, so let's say this is 1, and this is 2 here.
You say again, do you generalize the remark to products of those powers, or how do you get?
No, I just multiply the individual. It's not a generalization. I have for any factor, I have these expansions, then I multiply them together in the complete grouping.
They're in the right ordering automatically?
Yes.
Yeah, okay,
Yes, they have to be in the same ordering as the original factors, right?
Yeah.
Yeah. So compare 1 and 2 for the values xi. I take the coordinates of my phi h1 y1 hs ys. Right? Then by definition of the coordinate functions, the left sides are equal with choice of x. And so the right sides have to be equal, but this of course means, I mean these expansions were unique, I mean that the coefficients are equal. So get that phi I, yeah, I mean it's a little bit phi, I mean because of one cannot write down product signs because the order matters. I mean this makes the formulas a little awkward. Right, this is my x1, so over alpha 1 times phi r h1 y1 hs phi r over alpha phi r, sorry, alpha r is equal to sum beta y1 beta 1 ys beta s C alpha beta. So moreover, right? I mean, moreover, what do we know about the omega tilde? So let's look at right, I mean, in this expansion, we do know now that I mean, let's apply omega tilde to this, right? I mean, no, sorry, no, only to this here, to one such standard expansion, omega tilde of it. So on the right-hand side, right, I mean, this is the minimum of the valuation of the coefficients plus some I, alpha I, omega I. But this is now omega tilde of this thing. Now, we do know from the previous corollaries in the previous section that omega tilde is multiplicative, so we can exchange it with this product in the exponents. So we get sum beta j to s, and then omega tilde of an individual factor is omega of the group element. So it's omega hj. And so we do see, I mean, this is I'm not sure that it is strictly necessary, but I mean, I always find it better to reassure myself that certain things converge, also if in an intermediate steps. So you see it follows, hence, for any fixed alpha, we have that these C alpha beta individually, right? I mean, this only gives us that the VC alpha beta modified by this here go to infinity. But now we see that they individually, they go to, which, I mean, is needed, I mean, somehow, so that this makes sense, converges, because these are integers, so better they would go individually to 0. So, I mean, this may well come out somehow indirectly throughout these computations, but I find it better to reassure myself that this actually holds. So now let's simplify this. So let's specialize to alpha equal to what I call multi-index I underlined, which is simply the one which has a 1 at the i's place and 0 elsewhere. Right, so what happens? Of course, on the left side, only the i's factor here survives, and there alpha is 1, so we simply get phi I h1 y1 hs ys. And of course, on the right hand side, not much simplification, if any at all, happens. y1 beta 1 ys beta s. Just here I write, I underlined beta. And I mean, this has to be somehow our power series, right? If you look at the statement, right, the power series is actually supposed to describe this function of the ith power series. So this has to be our power series. So we have to see that this is a globally conversion power series. So right, I'm using this here. I mean, the minimum. So the individual thing here is bigger than this here. Here, of course, only we have now alpha is only the alpha I. The specific I is 1 survives. I can bring this term to the other side. So I have this is bigger or equal. Maybe I write the first omega gi plus some j beta j omega hj. And now this I rewrite artificially by inserting here the sum j beta j over p minus 1. And then I can subtract this here again, beta j omega hj minus 1 over p minus 1.
The moreover, should that be greater than or equal instead of equal? How?
Where?
In the moreover, the min.
Here you mean?
Yeah.
Why?
If you have h2 equal h1 inverse.
Yeah, and? What's the problem?
If H2 is H1 inverse, let's say, then what's,
I mean, this came from this here, right?
yeah.
Computing omega tilde of it. The left side is omega tilde of this here, and the right side is omega tilde of this here. And we do know that omega tilde is multiplicative. So omega tilde of this here is some beta j omega tilde of hj minus 1. And then we know for any group element omega tilde of h minus 1 is omega of h. I mean, if you have an inverse, actually, I mean, even if you, so what happened? I mean, it's still a non-trivial term, isn't it? I mean, even if you have h2 is h1 inverse. But I mean, who cares? I mean, even if this is 1 here, okay, then this just means that this is also 1. I mean, what's bothering you?
I need to think about it.
Okay. So now we use the so this will happen over and over again. There is this basic estimate. I mean, we will use this over and over again. There's this basic estimate of the p-adic valuation of the factorials. It's bounded above by n over p minus 1. Actually, I could write n minus 1, but then I have to exclude n equal to 0. So sometimes I will use it with n minus 1, and sometimes it's more convenient to relax it and use it for n. And hence, you see, I mean, this means here, these are the bounds, these are those bounds for beta j factorial. So if I correct my coefficient, if I divide my coefficient by beta 1 factorial up to beta s factorial, I still have that this is beta equal to minus omega gi plus this rest here. And this is here strictly bigger than 0, right? By axiom A. So this goes to infinity. So goes to infinity with beta. And on the other hand, I mean, look at on the other hand. Let's look at these polynomials here, f beta. Right? I just use the denominators here and write a variable. So it's the product over all j's, and then these denominators. And you see, this is a polynomial of degree theta with coefficients, of course, integer coefficients, satisfying that if I insert such a y1 up to ys, I simply get this thing here. So hence, so finally, the power series Fi defined to be the sum of all beta Ci beta over beta 1 factorial up to beta S factorial F beta. They do what we want. Right, I mean, they converge. Really makes sense because of this goes to 0, and if you insert by this formula, if you insert the y's, then you get exactly what you want. This formula instantly. Okay, so this is the proof. Give me 2 more minutes and then just to write down the corollaries. Because this is then now all very easy. Of G as a manifold does not depend on the choice of omega nor on the choice of ordered basis. Proof. Apply lemma to an ordered basis. I mean, you can do this in one step. To an ordered basis H1 up to HR for some other omega prime. And then, I mean, what the lemma tells you that the coordinates change is locally analytic. So the 2 charts, I mean, I've both, right, produce me 2 charts, but the coordinate change between the 2 charts is locally analytic. This is exactly what the lemma says in this case. And moreover, the multiplication map Mg is a map of manifolds. So apply lemma to the set H1 up to H2R, so 2R elements, where we just take the ordered basis twice. And then what you get is that right, I mean, then the power series, these functions are exactly the expression of multiplication in terms of these coordinates. And again, we see that it's locally analytic. It's always even globally analytic in a certain sense. It's always given by globally convergent power series. So together we can finally formulate any p-valuable group G as a natural structure of a p-adic Lie group, and of course the dimension of this Lie group right? Which can be read off, for example, by the dimension of the chart. This global chart, the dimension is R, so it's equal to the rank of G. Okay, so that's it for today. And then on Tuesday I start, which I think is a really beautiful theory, which will, I mean, so far we know that we can, by passing to a subgroup and modifying the p-valuation, we can make it saturated. But the actual much more beautiful construction, and in some sense canonical construction, is the opposite. We can always enlarge a group with a given p-valuation. We can always enlarge and extend the p-valuation in a canonical way so that the thing becomes saturated. This I will describe next week, because this is needed to show that there are rational value p-valuations.